Welcome to qnawire.
For this problem, we'll first write down the velocity of the circular orbits of the space vehicle around the moon. This velocity v is equal to the square root of g, the gravitational constant, times the mass of the moon m over the radius of the orbit r. Now in position A, the radius of orbit A is 1,400 miles. And so this is 7.392 times 10 to the power 6 feet. And so the radius of the velocity of the circular orbit A is equal to, we can substitute our values into the equation above. So g is 34.4 times 10 to the minus 9 in US units multiplied by the mass of the moon, which is 5.03 times 10 to the power 21 over r, which we calculated to be 7.392 times 10 to the 6th. And so the speed of the circular orbit A is 4.8382 times 10 to the power 3, and that's feet per second. Now we'll do the same for the circular orbit at B. The radius of the orbit at B, the circular orbit, is 1,300 miles. And this works out to 6.864 times 10 to the power 6 feet. So we calculate the circular orbit at B, and we'll calculate the velocity of the circular orbit VB2. And this is again g times m, 34.4 times 10 to the minus 9 times m, again is 5.03 times 10 to the power 21 in US units over the radius of the orbit, 6.864 times 10 to the 6th. And we get the speed of the orbit at B, the circular orbit, to be 5.0208 times 10 to the power 3, and that's feet per second. Now those are the circular orbits. So now we need to calculate the velocity of the transfer orbits from A to B. So we'll call that AB. Now for the transfer orbit, we want to calculate VA2. And this is the speed of the circular orbit, which we calculated VA1, plus the change in speed, delta V, at A. And so the transfer orbit A is equal to 4.8382 times 10 to the power 3 minus 86, the change in speed for orbit A. And hence we get the transfer orbit speed, transfer velocity from A to B to be 4.7522 times 10 to the power 3 feet per second. With this velocity, we will now use the conservation of angular momentum. The conservation of angular momentum tells us that mRA times this transfer velocity VA2 must equal to mRB times the transfer velocity VB1. And so if we rearrange this equation, we can find the velocity of the space vehicle as it approaches b, VB1 to be RA VA2 over RB. And all these values are known, so we can calculate this transfer velocity as well. So this is 7.392 times 10 to the power 6 multiplied by 4.7522 times 10 to the power 3 all over the radius of the circular orbit B, which is 6.864 times 10 to the power 3 in US units. And so this is equal to 5.1178 times 10 to the 3 feet per second. So we've calculated VB1, the transfer velocity, as space vehicle approaches point B or orbit B, and this is 5.12 times 10 to the 3 feet per second. Now next thing we want to do is calculate the speed change at B. So the speed change at B we'll call delta V B, and this is equal to the circular orbit speed minus the transfer speed, so VB2 minus VB1, and this is equal to 5.0208 times 10 to the 3 feet per second minus the transfer speed of 5.1178 times 10 to the 3 feet per second. So we'll just suppress the units there. Hence we get the transfer speed, or the speed change rather, at B to be minus 97 feet per second.